let's take two oppositely charged conducting plates. And we'll make them parallel to each other, and I'll make a little bit of spatial orientation so you can kind of see what's going on. And we'll make the note that plate 1 has the same area as plate 2. And let's just assume that their separation distance is, and now let's just call it D. From one plate to the other, they're oriented basically just flat to each other, parallel. And on one side, we have a uniform charge of its conductor. And on the other side, we have an equal but opposite charge. We'll deal with how you might get that charge equal and opposite at some point later. So let's call this positive Q and negative Q, something like that. So where we left off yesterday, we said that for this situation, as long as it's relatively, the distance of separation between the two plates is small relative to the dimensions of the sheets themselves, then within these plates, the electric field, and we can calculate that from Gauss's law, is a constant value which is related to the charge density, I'm going to say magnitude, divided by the permittivity constant, permeability constant, excuse me. And epsilon naught is 8.86.
Depends on your source.
10 to the negative 12 coulomb squared per Newton meter squared. I want to say 83 for some reason, man. I've been having this weird little elderly moments all week. Start feeling better. Okay, so we sort of start from there. We're pretty good with that. And the idea is that it's constant in between these plates. So here's what we want to think about. Now, we talked about, well, if I were to take a charge, put it in a uniform electric field, it would accelerate through at a constant acceleration. That's where we started 3 weeks ago with electric charge and this idea of electric field. And to this end, let's just think about what would happen. If I were to take an electric charge here, some value, I've got Q's here, so I better call it Q naught, or Q0. Okay. And if I were to place it in this electric field between these two plates, it's going to be pushed due to the electric force interaction between the electric field that's there and this charge. The amount of work required, or the amount of work associated with moving this electric charge a certain distance, say dx, a coordinate system here, so we're consistent. If it's positive charge, it would be in the direction of the electric field, negative charge opposite. But the work associated with moving this thing across be related to the electric force associated with this interaction, electric field, and dx. So I'll write it in its full form for now, which reduces to, for an electric force, Q naught E dx. That would be the work as it's moving across, as it's being driven across by this electric force. Okay, so now here's the idea. The electric field, first of all, or the electric force, excuse me, is another example of a conservative force. Because it's a conservative force, among other implications, is that it has an associated potential energy. Wouldn't have a potential energy if it were a drag or a frictional or a non-conservative force. But since it's a conservative force, there is a corresponding potential energy. And when the interaction that's associated with work due to a conservative force, then the work associated with that conservative force is related to minus the change in the electrical or in the potential energy associated with that force. So now I'm introducing a new term, E or U sub E, which is the electric potential energy. For the conservative force Fe. Now, if there's drag forces, then potential energy is not the only energy there. There's always these other things going on, but to the extent that it's a conservative force, we can say this. Okay, so what we're left with then is this, if you will, you consume or you transfer electrical potential energy, stored energy, if you will, as positive work is being done. Right? So you lose potential energy as you gain as work is performed. Gasoline, getting a car to make. So this is sort of where we are. Now, to this end, start playing some manipulations of this relationship. And first thing I'm going to do is I'm going to note that if I divided both sides by Q, I just take this relationship and divide by Q, then I can say that this quantity, E dx, in this case, should correspond to minus d, the change in the potential energy, divided by Q. In other words, potential energy per unit charge corresponds to the movement of a charge within an electric field a certain distance. This corresponds to this equation, only you're dividing the charge out. So you're not thinking of it in terms of a specific charge. You're thinking of it in terms of per unit charge. Just like an electric field is force per unit charge, instead of worrying about a specific force present or a specific charge present. So we have something that kind of looks like this. Now, here's where it kind of gets interesting. We have a name for this. The electric potential energy per unit charge. What we call electric potential. So, in general, potential energy per unit charge, we sometimes write it as V. And V corresponds to what we call electric potential. Not potential energy, it's potential energy per unit charge. Now, this one we've seen before, right? We've seen the letter V. You've seen it for volume, but anybody that's done any electrical circuits or otherwise also know V as voltage. Think about the units of this thing, they would be units of joules per coulomb. The definition of a volt is 1 joule per coulomb. So when you think about a battery with a certain voltage rating between the positive and the negative terminals of that battery, what that means is that if you were to push 1 coulomb of charge, we had a battery that had these terminals we were to plug a wire in there, the generation of, or the movement of 1 coulomb of electrical charge from one side to the other, and really it's the electrons going backwards, but we typically think of it as positive charge, has an associated mechanical energy or an associated energy requirement of 1 joule. It takes 1 joule of work, or there's 1 joule of associated work for that 1 coulomb of charge to transfer from one end of the battery to the other. Now, we don't usually think in terms of how much charge we're drawing from a battery or any power source. We just think of it in terms of rates of flow and current and whatnot. So there's no need to talk specifically about a particular energy rating for a battery. We talk about energy per unit charge. That way, the amount of energy is only associated with the amount of charge drawn at any given time. That's why we use voltage. So that's the idea of the volt. And if we just then think about the potential energy per unit charge in terms of volts, then we're left with a relationship that looks like this. The change in voltage dV is oppositely directed to the product of the electric field and the displacement. So a forward movement would correspond to a negative potential difference change. Or a forward positive E dx would correspond to a drop in voltage, positive to negative. Oh, that's what current does. It flows from positive to negative. See how these things start interrelating. So, turns out to be a little curious when you look at this for this type of an arrangement. Because we have a constant electric field, because of the nature of this type of a induced charge interaction, we can rewrite the electric field in terms of the surface charge density and epsilon naught. So now we can relate voltage differences, if you will, potential differences, electric potential differences, dV, in terms of the charge properties of either of these conducting plates and the distance of movement as a particular charge were to slide across between the plates. That make sense? And the surface charge density could be written as the amount of charge on either plate per unit area. Got an epsilon naught I have to throw in there, and then I have a dx on one side. So everything now sort of reduces to this. There'll be a whole bunch of stuff we'll talk about with respect to electric potential in chapter 24. But for now, as we look at this, what we have is an electric field interaction or putative interaction, hypothetical, with respect to moving some charge between these plates in this electric field. And it's related to this electric potential. And all of these properties of the plates themselves. I'm going to rearrange this into a slightly different form. I'm going to take Q. Well, first of all, let's apply this over the whole thing. If I think of any charge, or if I think of the path from the positive plate to the negative plate for any amount of charge, then I can evaluate the potential difference, the voltage, over any little segment here as I move across. And in doing so, it's the equivalent of evaluating Q over A epsilon naught dx as we go from one side, if you will, to D.
With a negative there somewhere?
Yeah. And really, I'm going from the potential difference at the positive plate to the potential difference at the negative plate. Or I'm sorry, the potential at the negative plate. So as we go along here, there's an associated delta V between any two regions. And I can look at the extreme as I look at what the potential is at one or near one surface, and the potential difference near the opposite face. In this case, I've got these bad ones, plus and minus, right? So if I evaluate the one side, it's delta V, if you will. On the other side, it's minus Q over A epsilon naught D. Okay, that's a beautiful little exercise, whatever. Physicists like to look at these sorts of things. But I'm going to rearrange this a little bit. First of all, I'm going to note that the magnitude of this will correspond to this quantity here. Okay, so I'm not going to worry about the positives or negatives. I just want to know something about the absolutes. In the same way, we would look at a battery and say, oh, it's 9 volts. I'm not going to worry about the positive, negative aspect at this point. It will just be determined by which charge plate I'm looking at if I were to evaluate it, right? Sigma will be positive for one face, negative for the other anyway. Q will be positive or negative. Depends on which one I look at. So I can look at absolute values and not lose any conceptual implication. So what I'm going to do then is I'm going to rearrange this. I'm going to divide both sides by delta V and bring all the other stuff over. So Q over delta V, write it as this. At some point we'll stop using that. We'll just call it magnitude V. Corresponds to epsilon naught A over D. In other words, all of the constant quantities on one side and all of the potentially changing quantities as you move charge or you accumulate charge between the surfaces, everything, all of that's on the other side. In other words, these are the things that can change by separation of charge, by manipulation. These are the physical properties of this system. The cool thing is, this is all constant. And because it's constant, it requires that there is a formal linear relationship between Q and delta V. So Q will have to vary linearly with this delta V term, because the ratio has to be a constant value. Now, because of that, we give a special definition to all of these, to this relationship that's associated with separation distance, surface area, and then the permeability constant. We call this the capacitance. The term capacitor, capacitance, stems from the relationship of Q, or charge, per unit volt, which is determined by the physical properties of the conductors that are interacting by their charge. It's kind of cool. So we call Q over delta V capacitance. So we give it a letter C. And And the capacitance is really the physical property due to the interaction between these conductors. And it depends on where they are, it depends on their size, and it'll even depend on their geometry at a more complicated level, but at least for these two parallel conductors. I'm just going to call it charge. It's an electric interaction. It's a lot to write off to the side, huh? Okay. And this quantity is related to the surface area of the charge is spread out, inversely related to the distance and separation, and then this physical constant. So this epsilon keeps showing up. Now can you imagine writing this epsilon as A over 4 pi k times d? I mean, it's just much easier to use epsilon. There's a lot of the reasons why k is easier for Coulomb law calculations, but at some point you just want to use epsilon. It's much more fundamental. So, and specifically, this is for a parallel plate capacitor. This is only specifically true. This quantity will just be indicative of any two conducting surfaces that are close enough to interact in an observable way. This quantity is just due to the physical properties of a parallel conducting plate system. So we've got a little bit of things here. Now let's note, first of all, the assumption is we've got empty space in between. So we assume that the surfaces are parallel and facing. And we also assume the space in between is either air or vacuum, technically vacuum, but air is close enough. Can't tell the difference. Because when you have air, the gas particles are so thin and sparse, low density, that for all practical purposes, it's empty space. This is what we're going to explore today. This is a quantity that we're going to look at specifically. I just want you to see that we're not there in the class. That's very organically related to the basic ideas we've been looking at up to this point. It's amazing we're just looking at mathematical relationships and rearranging them. What you sort of come up with something. Now, one little difference we'll make here. If you were to fill this with something else besides air, now there'd have to be a requirement. You have to fill it with something that won't allow the charge to flow, because if the charge can flow, it won't separate. But if we could fill this region with an insulator or a non-conductor so that it doesn't, so charge doesn't flow, but it's not empty space, then the physical constant or the physical capacitance will change. So if the plates are separated with an insulator, sometimes we give insulators another term, and this comes from other aspects of the study of this subject. Sometimes we call it a dielectric. It's filled with a dielectric. This relationship changes ever so slightly. This part stays the same. But now we throw a little extra constant in there. Call it kappa. It looks like a K, but it's a kappa. And this kappa, what we call a dielectric constant, very, very original. In other words, a unique dielectric will have a physical property, kappa, which is its dielectric constant. And as a general rule, the dielectric constant will always be greater than or equal to 1. And the reason is the dielectric constant for vacuum or air, in fact, is defined as 1. So everything is relative to vacuum, if you will. The electrical field properties change when you put something in between. Why? Kind of makes sense if you think about it. Why? What would happen if you took any substance and put charge on one side and an opposite charge on the other side? What happens to that substance? If the charge can't physically move, what happens to it then? Think lab 1.
Reduce it. Doesn't become charged.
The charge is separated, but the molecules inside polarize. So the individual molecules, minus plus, align themselves based on their mutual attraction and repulsion to the charges on either side. So why does the capacitance property, this Q over V relationship, vary when you put something other than air in between? It's because when you have air or vacuum, there's nothing to induce. But when you put other things inside, now you get a rearrangement of the charges, even if they don't physically move, but you get a natural charge separation, kind of like when you take a charged rod and put it near water and water bends, or we could make the meter stick move with the charged rod. It's because the charge is polarized and you get an induced electrical property inside, electrical field inside, and it changes the capacitance. This quantity here, by the way, the dielectric constant times the fundamental permeability constant, we sometimes call that the effective permeability constant, or the effective epsilon. So, put it over here. So if we were to insert a slab of dielectric in here with some kappa value, that up inside there, the effective permeability constant would be related to kappa times epsilon naught. So there's nothing new here, but it's just another terminology. Kind of like light moves differently through plastic than it does through air. It slows down as it's going through a plastic transparent sensor. So the dielectric constant is kind of like an index of refraction. In fact, it's related in some way. So that's what we're going to look at today. We're going to take a pair of charged plates and fill them with material inside, plastic essentially. And we're going to measure the capacitance, should look down here, as we vary separation distance, and use that information to try to obtain a value for the effective permeability, which we can use to estimate the dielectric constant. getting dangerously close to electrical circuits now. And this subject here, I've talked before about how much I love thermodynamics. It was this subject and this discussion in this class when I was on your side of the table that was the linchpin to my final decision to go into physics as an academic field than electrical engineering. So I got really tired of seeing equations without no justification, but you got to solve them. It was trying to understand the basis and how they were related to physical things at a very basic level. It was just like, God, that's obvious. Whatever you do as a profession, you got to understand this stuff. And that was my personal turning point. I mean, literally, there's sort of that existential moment where you literally change directions in your life. This was mine. So, our objective today is twofold. It's to use capacitive measurements. I'm going to say it this way. C versus separation distance, D, measurements. To, 1, determine the effective permeability. Epsilon. Two, to estimate dielectric constant. Now, unfortunately, at this point, we're not going to be doing specific charge voltage measurements. We have a device that does it for us. It turns out there's all kinds of other properties. Some of you at least, if not most, have had some electrical circuits at some point. You know that you can charge a capacitor as it discharges, as a certain shape that it has when it discharges. All kinds of properties to the way capacitance works, which we'll get into. It's a whole chapter. But we're going to use a little device. It's a multimeter. This is a typical electrical device any electrician or electrical engineer ends up using. It measures voltage, it measures current, it measures resistance and other circuit properties. But certain ones, not all of them, will actually measure capacitance directly. So if you've ever used one of these digital multimeters, there's one fundamental difference between this device. We don't need log or prototate other than graphing, by the way. We'll use it for graphing. You can do that at home theoretically, but it might be better to do it here for make sure we get everything straight. I'll hand these out right now just so you can see what it is that I'm talking about, and then we'll get the stuff set up for them. Yeah.